Next, we will discuss how the limits can be used to redefine continuity of a function at a point. Continuous functions are the object of interest for many reasons. One of the main reasons is that continuity is a very nice property, and many theorems in calculus will begin with the words let f of x be a continuous function. A function can be continuous at some points and discontinuous at others. Visually, it is a pretty straightforward task to identify whether a function is continuous or not at a point. Let's recall the definition of a continuous function. We were told since early math classes that a continuous function is such that can be drawn with a single continuous stroke of a pencil on a piece of paper. What else do we know about continuous functions? Continuous functions visually look very simple at any point. So let's pick some point A. The left-sided limit exists, and the right-sided limit also exists, and they are both equal. Therefore, the two-sided limit exists. But what is it equal to? From the image, it is pretty clear that the limit matches the output of the function at the point. In other words, to find a limit of a continuous function at a point, we simply evaluate the function at that point. We're now going to use this fact as the definition of continuity. We say f of x is continuous at x equals a if and only if the two-sided limit of the function at a exists and equals to the output of the function at a. In other words, the left-sided limit exists and is finite, the right-sided limit exists and is equal to the left-sided limit, and both of them are equal to the output of the function at that point. Now let's discuss what could possibly go wrong with the definition of a continuity of a function at a point. It is possible that a function has the left-sided limit and the right-sided limit that are equal to each other, but not equal to the output of the function at the point. In such a case, we say that a function has a removable discontinuity. For example, the following rational function with the following graph at x equals 1 has the left-sided limit, the right-sided limit, and they both are equal to 1/2. But the output of the function at this point is not defined. Therefore, we have a removable discontinuity. It is also possible that a function has the left-sided limit and the right-sided limit that both exist and finite, but not equal to one another. In such a case, we say that a function has a jump discontinuity, regardless of what the output of the function at the point is. For example, the following function with the following graph at x equals 1 has the left-sided limit that is equal to -1 and the right-sided limit that is equal to 1, which is different from -1. Thus, we have a jump discontinuity. It is also possible that a function doesn't have either the left-sided limit or the right-sided limit, or both. In such a case, we say that a function has an essential discontinuity, regardless of what the output of the function at the point is. For example, the following function with the following graph at x equals 1 doesn't have the left-sided limit and the right-sided limit is infinity. Thus, we have an essential discontinuity. Finally, we extend the definition of continuity at a point to an open interval. f of x is continuous on an open interval I if and only if f of x is continuous at every point on that interval. Now, using the language of continuity, we can say that the following function has an essential discontinuity at -1, a removable discontinuity at 1, and a jump discontinuity at 2, and it is continuous on the following interval. We discussed how the limits can be used to define continuity of a function at a point or on an interval.